Thank you and good afternoon. So I'm Nick Smith. I work as a technology strategist at Pkcs Security. I've spent the last 5 years maintaining, writing and using crypto APIs. So this is a bit of my journey really. So today I'm going to start by talking about the history of some of these APIs and why we've got them, and then move on to what the state of the art in crypto API design is, and then conjecture on what might cause us to evolve in the future. You'll have to bear with the tenuous link between crypto APIs and evolution, and I apologise to any microbiologists in here. So, where do crypto APIs come from? If you go back to the mid-90s, there were a number of things that happened. So, one of the big things that happened was at Netscape, if anybody remembers them, they defined the first SSL protocol. And quickly followed by version 2 and 3. And this gave birth to a library called SSL EAY, which we now know as OpenSSL. Now this library started to support SSL and to be able to provide secure communications between browsers and servers. But one of the outputs of it as well was a cryptographic API that could be used by application developers. Now, one of the interesting things about libSSL EAY and now OpenSSL is the size of the library and the complexity in using it. So, about 20 minutes ago, I had a look at my local copy, and there was around 3,000 functions exported by that library alone, which is incredibly complex to negotiate and to manage, and is one of the reasons why things like LibreSSL and BoringSSL appeared, not just because of Heartbleed, because the complexity in these libraries has been increasing ever since the mid-90s without significant refactoring. Other interesting things about this library is if you build and configure it locally still, you will get functionality like MD4 and MD5, as well as RC2 and RC4. All of these have been questionable for 10, 15 years. So there's a lesson there. Anybody who's writing cryptographic applications, make sure you configure OpenSSL correctly, or LibreSSL. Don't just assume what you've got is secure. So around the same time, there was some other standardizations and libraries that appeared. So the most notable, and one that I am very familiar with, is Pkcs 11. Most people won't know what Pkcs 11 is, but it's quite widespread in use. It's a software interface for abstracting hardware crypto modules. So when I say a hardware crypto module, this might mean a smart card or an enterprise appliance which has been hardened to provide cryptographic acceleration or increased security. So if you look at that in comparison to OpenSSL, it has much fewer functions, but has a much more limited scope. On the plus side, it is more coherent and generally easier to use, but requires hardware modules. So then slightly later, as is always the case with Windows, Microsoft released their crypto API called CAPI, so Crypto API they got. But they have in fact updated that in crypto terms rather recently, in 2006, with the release of Vista and their Crypto Next Generation library. Now, one thing you'll notice is a lot of these libraries and interfaces came out around the same time, and they're all C-based APIs. And that is because at the time, C was the systems programming language which most people were still using. However, the world has changed significantly since 1994, 1995, but the crypto APIs that are available to use have not. So whilst modern day practice is to use things like JavaScript for application development, you'll still find most APIs are thin shims on top of OpenSSL and don't do a very good job of abstracting the complexities of that library. So we move into today, and so we'll talk about some of the problems that we're now experiencing as crypto API designers and implementers. So a good example is quantum cryptography. and being able to be quantum safe. So Google started an experiment last year to add quantum safe key agreement to TLS, but using an algorithm and some premises which still require much more cryptanalysis. So what they were trying to do is make sure that TLS is future-proof, but maintain the security level it has now with things which are comparatively untested. So to do that, they ended up combining cryptographic primitives and again, significantly increasing the complexity of APIs. So the way they did this was they took a traditional key agreement algorithm and a new post-quantum one and exchanged two keys and then combined those two keys to form one quantum resistant as well as standard security key that they could use for communication. But this is just an example of how the difficulty in crypto APIs, and now that we're living with some decisions from the early 90s, how it's becoming much more difficult for us to retrofit these things into the modern web, into modern languages. So if we take what Google have done and extrapolate that a bit, there is no doubt in my mind that we will need to start providing digital signatures which will be quantum resistant. So often governments will build services which they hope will have a lifetime of 20 years. Some people think that there may be quantum computers in 20 years, so we need to think about the security. So if we need to start signing things with quantum resistant algorithms which are not yet proved, as well as maintain security now, we're going to have to sign them twice. And what that means is we've got a real difficulty because all our APIs, all our serialization formats expect a single signature, not two signatures. So we're at a crossroads about what are we going to do? How do we fit the current world with some of our previous decisions? It's not all bad news, thankfully. So there has been some evolution in the area of crypto design. And so I'll talk about two things. So firstly, there's a set of new serialization formats which I'd recommend everybody who's writing cryptographic applications to look at, and they're called the Jose standards. So previous standards, which were based on a protocol or at a serialization called ASN1, which was a binary encoding. New ones are based on JSON. And new languages, JSON is a native data structure within those fields. And so what we've been able to do is bring some of get rid of some of our technical debt and bring some new serialization techniques which are now native to modern applications to the new world. The nice thing about these is they're human readable. There's lots and lots of tools that you can get to extract them and to look at them. While if anybody who's had to work with X509 certificates will tell you that life has never always been that simple. Unfortunately, they didn't get rid of X509 for backwards compatibility reasons, which is a real shame. So that's why I say we've evolved somewhat. However, the latest and biggest standardization in the world of crypto APIs has been by the W3C, the guys behind standardizing the web, and they have come out with a brand new crypto API for JavaScript, which is very nice. It's got a very modern pattern for design in there. So before, if you again ever use OpenSSL, Pkcs 11, you are presented with a very flat expert interface. If you don't know what a nonce is or why you shouldn't reuse them, you should not use that interface. Thankfully, the guys in the web crypto world thought about this and said, okay, modern application developers are going faster and faster. They're not security experts or cryptographers. We're going to split the API. So there's a higher level API, which is secure by default. And then there's a lower level subtle API, which leaves the gun loaded for you to blow your foot off should you wish. Don't use it unless you know what you're doing. So we've had some evolution. And that evolution's been in the last couple of years, and that has come about by the change in the systems that we're using. And as we're moving more and more towards the web, we're having to evolve. So the web, and actually cloud, may be the thing that actually forces us to completely evolved from our decisions from the mid-90s. So one of the interesting problems that people have now in business and what developers are expecting now is to consume services. They don't consume C APIs anymore. So what we're looking at and what we think is going to happen is you're going to get crypto as a service APIs. No longer will you worry about OpenSSL. Well, you will, but I'll get onto that. No, but you will be doing your crypto on an external server in the cloud, somewhere else. It will be using APIs, just like your storage APIs. No longer do you store files. You shove things in your S3 bucket on AWS and forget about them. And so we're going to look at an evolution towards this model where, again, instead of using OpenSSL, Pkcs 11, you're going to start to use remote APIs. That has a number of nice functionalities, such as you can centralize your crypto processing. It makes things like key management easier, but brings a whole new set of attacks into play. So if you're using a service, are you really sure your TLS stack is secure? Really? Because most people's aren't. And also, you start to have to bring things like stronger authentication and authorization, which an application level has previously been quite poor. And we've seen a few talks today about securing APIs and how difficult that is. When your API is your crypto service, you really do have to think hard. But going forwards, I think what we need to move on to as an industry is to provide high-level APIs, not so many low-level crypto APIs, which are secure by default. No longer do we want to say, here's how you encrypt and this is how you write a file. We need to combine them and say, this is how you write a secure file, this is how you upload. And so that's where I believe the industry will go, and we will move higher and higher up the stack to provide security. My last bullet point there is about, can we provide automated data security based on AI? Can we identify threats and perform automatic remediation and encryption? I'm yet to be convinced, but that's where I think we might be going. Thank you.